Today we're going to talk about section 7.5, roots and zeros. We've talked about zeros before. We've said that they're the same as x-intercepts. They're also called roots. So whenever you hear zero, root, or x-intercept, it all means the same thing. So the following statements are equivalent. A real number r is a root of the polynomial equation. P of r equals 0. That means when you plug it in, you get 0 out. R is an x-intercept of the graph of P of x. X minus r is a factor. That goes back to our factor theorem. We said if something was a 0, that means we got 0 out with our synthetic division. When you divide the rule P of x by x minus r, your remainder is 0, and r is a 0 of P of x. The fundamental theorem of algebra, obviously this is pretty important, says every non-constant polynomial function has at least one 0. Where 0 may be a complex number. So there's always at least one solution to an equation. The corollary says every non-constant polynomial function of degree n has exactly n zeros, including multiplicities. So that means we might have an equation, we might get the answers 1, 2, or 1, negative 2, 1, and 2 out. Well, 1 would have multiplicity 2. It would be listed twice, but this would be 4 solutions, 1, negative 2, 1, and 2. So that would be a degree 4 equation. Okay, solve each equation, state the number and types of roots. So this goes back to algebra 1. Solving this equation, I add 10 to both sides. I get a equals 10. So when I ask you how many answers there are, there's one solution. So there's one root. So we say one real 0. You could also use the word root. This next one, it's x squared. We're going to try to factor. I know I need x and x to multiply to be x squared. I need negative 48 at the end, so I need negative 6, positive 8. This way my outer and inner terms do combine to be positive 2x. Set each piece equal to 0 and solve. So I get x equals 6 and x equals negative 8. That means I had 2 answers. So we say there are 2 real solutions. So 2 real zeros. Okay, the next one. I have an a squared term. So you think you would need your 2 sets of parentheses to factor. But actually there's only 2 terms. We pull out what they have in common, a 3 and an a. When I do that, I have a plus 6 left. Set each piece equal to 0 and solve. Now this 3a, I could have just written a equals 0 there because the a is the only thing that's making it equal to 0. You had 3 times something else equals 0. So a was what could have been 0. Or a could have been negative 6. Again, there's 2 answers, so we say 2 real zeros. On the next one, I can use the difference of 2 squares. So it's going to be y squared plus 4 times y squared minus 4. Now the y squared minus 4, that's the difference of 2 squares as well, so we can factor that one. But the y squared plus 4 stays as it is. It doesn't factor. Okay, set each piece equal to 0 and solve. I have y squared plus 4 equals 0. I have y plus 2 equals 0. Y minus 2 equals 0. When I subtract the 4 to the other side, I get y squared equals negative 4. So square rooting both sides. The square root of negative 4 is 2i, so I get plus or minus 2i. So there's 2 answers there, positive 2i and negative 2i. This one gives negative 2, and the last one gives 2. Okay, so there are actually 4 solutions there. I have 2i, negative 2, and positive 2. So there's 4 zeros. But when we talk about the type of zeros we have 2 imaginary. You could also call them complex, and 2 real. Okay, so 2i and negative 2i were the imaginary solutions, 2 and negative 2 were your 2 real solutions. Okay, the last thing on this page, it says the complex conjugate root theorem. it says if a plus bi is a root of the polynomial equation, then a minus bi is also a root. And this just goes to our, we had positive 2i and negative 2i. If one was a solution, the other one's a solution. That's all that's saying. They go in pairs, and they're called conjugates. Now this takes you back to chapter 5 on your exam. I asked you guys for the conjugates of certain things. So I would give you 3 plus 7i, and I asked you to list the complex conjugate. So you would put 3 minus 7i. Then I tried to trick you. I said, well, what about if I had 1/2 I minus 3/4? Its complex conjugate was negative 3/4 minus 1/2 I. So all you do is change the number in front of your I part. So that's how it went from positive 1/2 to negative 1/2. Okay, the part that was real, so the part that didn't have an I, that stays exactly how it was. It was negative 3/4, it's still negative 3/4. So if I had 5i minus 6, it'd be negative 6, so same as what it was, and then a negative 5i. So it becomes the opposite of what it was before. Okay, so just basically change the part in front of your I. Okay, write the simplest polynomial function with zeros 3i and negative 1. So that complex conjugate theorem says if I have a 0 of 3i, I also need negative 3i. Okay, they go in pairs. So if I have one, I need the other one as well. So we've written polynomials with certain zeros before. If I have a 0 of negative 1, that means I need x plus 1. Because basically when I plug negative 1 in, negative 1 gives you 0. Okay, if I have positive 3i as a 0, that means I need x minus 3i. So if I plug 3i in, I get 0 out. If I have negative 3i, I need x plus 3i. Okay, so this is my polynomial. It's factored. We need to multiply it all out. Now, don't make things messy and don't multiply, just always the first two together. Because if I multiply these first two things together, I'm going to have things that have i's. It's going to be a really long polynomial. It's going to be a mess to multiply by the x plus 3i. So I always multiply the parts that have the 3i and negative 3i together first. So we're going to FOIL here. Okay, so I have my x plus 1 still out front. When I FOIL, I get x times x is x squared. My outer is x times 3i, so plus 3ix. My inner is negative 3ix. And my last is negative 3i times positive 3i, so negative 9i squared. Okay, this is nice because the 3ix and negative 3ix cancel. And then we know that I squared is equal to negative 1. So I now have negative 9 times negative 1, which is positive 9. So I have x squared plus 9. Okay, continue to FOIL, so I'm going to FOIL this part. So when I FOIL, I get p of x equals, first is x times x squared, so x cubed. Outer is plus 9x. Inner is plus x squared. Last is plus 9. I'm going to write it in descending order, so I get x cubed plus x squared plus 9x plus 9. That's your polynomial. Okay, Descartes' rule of signs. So suppose we have a polynomial with real coefficients. It's kind of confusing when you see it all written out like this. But it says the number of positive real zeros of f is either equal to the number of variations in sign of f of x or less than that by an even integer. Second part says the number of negative real zeros of f is either equal to the number of variations in sign of f of negative x or less than that by the number, or less than that number by an even integer. Okay, so when I say positive real zeros, that means on your axis, that's the number of times it crosses on the positive side of your axis. So these would be positive real zeros. When I say negative real zeros, that's the number of times it crosses on the negative side. Okay, so this Descartes guy, he's a philosopher, he's a mathematician. He's the one that came up with the Cartesian coordinate plane. He's the one that said -3, 2 would be right here. Okay, so it's a pretty useful guy. Well, he came up with this theorem. He said, basically, if you know that you only have one possibility for a negative real zero, you don't want to try any other possibilities. So it's really helpful. It will make more sense, I think, in the next section for you guys. But let's talk about how to make this chart. Okay, let me stop it here. I'm out of time.